Okay, so for this first one, we're going to find ES. So we're looking for this component right here. We're going to use Kirchhoff's voltage law, right? What goes up must go down. We see we have a voltage source here. This has to be the positive and the negative side. And for this one, we don't know whether it's a rise or a drop, but that's what we're going to solve for. So what we could do is just pick a direction and just say, that's the positive, that's the negative side. And if we get the polarity wrong, then it just means the terminals are actually swapped. This right here is R, right? It's in ohms. There's I. So we can solve pretty quickly for each of the voltages across each of these resistors. We know the current's flowing this way, which we can then say that these are going to be drop. A current will always, or a voltage will always drop in the direction of positive current flow. So if this is positive current flow, it says 2 milliamps, it doesn't say negative. So therefore, this will be a voltage drop across this is what we know. But we need to solve for each of these with our favorite law, right? So for the first one, V1, I'll just label these 1, V1, V2, and V3. So for V1, we have 2 milliamps. That's the current flowing through it, times R, 12 kilo ohms. That comes out to 24 volts. V2, we repeat the process. We have 6 times 2 is 12 volts. V3, we have 3 kilo ohms, so 2 times 3 is 6 volts. So now using Kirchhoff's voltage law, we say that assuming that these two are in the same direction, see how the positive is in the direction here as this one. If we look at the little arrow, it's going from the low side to the high side. If we follow that arrow, low side to the high side. So that means these are both rises. ES plus 62. And then we can say the drops. Well, these are all 3 drops. And so we have 24 plus 12 plus 6. All 3 of those together comes out to 42 volts. So if we're solving for ES, that'd be 42 minus 62. And according to the way that I drew it, it's negative 20 volts. And that's because I drew this positive in the same direction as the source. So if you got 20 and you drew your terminals the other way, that would also be correct. So there's number 7. Number 10 is right here. This one is actually probably easier than the last one. It's fewer steps. These are just interchangeable. If I just look at these terminals and whether it's opposing or going with it, then I can add up each of those rises, right? Or each of these voltage sources. So these voltage sources together, this one's going this way, so we'll call it positive 12. We keep following. This 3 volts right here is in the same direction. Its terminals are in the same direction as the 12, so it's positive 3. And we follow around to the 6. Well, right here we can see that this is where the positive touches the positive. And so it's like this 6 volt is receiving a charge from these other 2 that are charging it along with the resistor. So this would be a minus 6 volts. So we'll call these our rises, the rise. And we've said negative 6 because it turns out that its terminals oppose it. So if you put it with the drops, that would be fine. But since we want to simplify it, it's probably easiest to put these together and we get 9 volts. We have to draw it in the same direction that we drew the 12 in the 3 because those are the positive. So in order to maintain the positive, we have to keep the terminals in the same direction. Now for all the resistors, the resistor totals, we can just add them up. 27, 33, and 18 comes out to 78. So I can simplify with a single resistor, 78 kilo ohms. If I wanted to find the current flowing throughout it, well, I is equal to V over R, favorite law, Ohm's law. And so we can put 9 volts divided by 78 kilo ohms. And your I should come out to 115.4 microamps. Micro is the Greek symbol mu. I'll draw it over here. Mu, and it's kind of like a cursive looking U. If you just draw a cursive looking U, lowercase, then that is the Greek symbol mu. The last one, it kind of got easier as you went along. So from this one, we're just looking from A to B. Here's A, here's B. So this is a voltage divider rule problem where if I'm looking at the voltage divider rule equation, it says Vx is equal to Veq. That Veq you can think of as like what is being shared amongst the Req resistors, which is must be series. VDR must be for series. You can use KVL anytime, but in order to use voltage divider rule, it's only for series elements. And so these three are all in series, and they together make up Req. You probably saw in the video the box method where you can box three resistors together like that, or just box any number of resistors together and say that equivalent is what is inside that box. And so we're looking for the one across Rx. So we're looking for VAB. Back to the subscripts, that means that this R needs to be the RAB, right? If X is here and X is here, then AB is here and AB is here. In this case, the voltage being shared amongst each of those is the total. That's not always the case. It's always between what the series element nodes. So here's where the series begins, here's where the series ends. And if you notice from here, well, that is the same voltage drop. So 110 volts is being split up amongst all three of those. We're looking for RAB, which in this case is R2. So we have 30, and then we have 50 plus 30 plus 20. Altogether, that gives us 33 volts.